Hi everybody. So we are going to start with chapter 15, Equilibrium. I tried to wait until my voice was a little bit better before I recorded this. So here's the homework for this week. And then next week is here. So we got 2 weeks of Equilibrium. I'm going to break it up. The math can get pretty intense for this, so take your time. Make sure that you write down the ones that you want me to help you with. Okay, so our objectives in equilibrium, this chapter, is to define what equilibrium is. We want to be able to write equilibrium expressions and understand what K means, which is our new variable. We're going to convert between Kp and Kc. Kp is for pressure and Kc is for concentration. They're both equilibrium constants. It's just one is for pressure and one's for solutions, or one's for gases and one's for solutions. We're going to use rice tables. This skill, this method, is very important for the rest of the year. So make sure that you become very comfortable with making a rice table and knowing what to do with it in order to solve a problem. We're going to solve for equilibrium concentrations, and then we have a lab. All right, so what is equilibrium? Equilibrium is when you have a reaction happening in the forward direction. So you have a reaction that proceeds forward, right? From reactants to products. But that reaction can also turn around and go backward from products to reactants. And so what will happen is a reaction will start, the reactants will start forming products, and then as you build up a concentration of products, now your products are going to start and react. And so what you end up getting is this double arrow for the reaction going forward and reverse. Okay, so the reaction can proceed in the forward direction, and then it can also go back. When you reach a point where the rate going forward is equal to the rate going backward, so they are at the same pace, the way that the reactants turn into products will go at the same timing as the products going back into reactants. That's when you've reached equilibrium. So it's a dynamic process, meaning that it's like a treadmill where you're running at the same miles per hour that the treadmill is going in the opposite direction. And when you reach that chemical equilibrium, you are exactly matched up with the pace of the treadmill. But you're still moving. You're not sitting there doing nothing. So it's dynamic because that reaction is ongoing. It occurs when the reaction and its reverse reaction proceed at the same rate. It's very important to note that we are talking about a rate here, not about actual concentration of reactants and products. You can be at equilibrium and have a different amount of reactants and products in your container. It's just that the rates are the same. So again, the concentrations of the reactants are not necessarily equal to the concentration of the products. It can happen, but that's not what this means. So we're talking about the rates that are the same, forward and reverse. So here's, what I just did, reactants to products, products to reactants. So this rate, the rate of the forward reaction, rate 1, and this would be rate 2, are equal to one another. But you could have different amounts of reactants and products. Okay. So here is an example. You have N2O4 going to NO2. That's your initial point here for N2O4, and we don't have any products, so there's no rate of that going backwards. So the forward rate starts at some number, and it starts going really quickly. As your reactants start to react, now your products start to build because you've created more, and so their rate of reaction moving backwards is going to start to increase. So there eventually, this starts slowing down because you've used a lot, and now there's not as much in there. And then the reverse starts slowing down because you've used a bunch of that, and now they get to a point where their rates are the same. And at that point, that's your equilibrium. Again, this is not concentration, this is your rate. Because this is your rate law, right? For the reverse, and this is your rate law for the forward reaction. Okay. In a system in equilibrium, both forward and reverse reactions are happening. Like I said, it's still going. The treadmill is still on. You're still running. You're not going anywhere. You're not going forward or backward. You're staying in one spot, but you're still moving. Okay. So we actually just did this, but we're gonna say if this is an elementary step here, right? And there's just one of them. Okay. Since it's the elementary step, I can use the stoic as my order. I'm just going to put a 1 there, even though, we don't need it. So then for the reverse, again, elementary step. Okay, so this is reverse, and this is forward. Okay, so at equilibrium, my rates are equal, meaning my rate laws are equal. We will rearrange it. Here's your product. Okay, with this little 2 up here. Here's your reactant. And your K's are here. What we do is we can combine the K's because they're both constants and have a new K, and it's a capital K, my equilibrium constant. Okay, so this represents the ratio of my rates, or ratio of the rate constants for the forward and reverse reaction. KEQ can come in many forms. You might see KC, that's for concentrations. You may see KP, that's for gases when we're dealing with pressure. KEQ just means equilibrium. But they're all the same thing, they're just specified for different types of reactions. All right, so if you have a reaction, very general, A plus B goes to C plus D, where the little ones are your stoichiometry. This is what your equilibrium expression will look like. Reactants are on the bottom. Products are on the top. And your stoichiometry goes where your exponents go. Okay, so if I'm given concentration, which this little C here denotes that I'm given concentration, I'd put the concentration of C to the C power, concentration of D to the D power, over A to the A, B to the B, and I can calculate what my equilibrium constant is. Okay, so that's my equilibrium expression. So here's your equilibrium constant, and then information from the actual reaction. All of these are equilibrium concentrations that we would put. So I want you to go through, I'll do A for you, and then I want you to pause and just do the rest of them. So for A, products over reactants, oh my goodness, so K is equal to. So first I start with my product, put that on top. That's my exponent. Then this guy goes on the bottom, that's my reactant. Here's my exponent, and that's my K expression. That's my equilibrium expressions. They're all gases. So I could also do a KP for this one. So let me just show you. If I had asked for specifically the KP, you would do the pressure of O2 over the pressure of O3 squared. That's for KP. This one could be KQ, KC, either one. When you are dealing with pressures, which is if you have like an all gas reaction, I don't care. For now, just stick with the KQ, but that's just for your info how you would do it if I asked for KP. All right, so try B through E. Here they are. Here's the answer to B, C, D, and E. If you have ions, just make sure that you include the charges. So if you look at E, you have cadmium bromide with a 2 minus charge. And then underneath you have cadmium 2 plus and Br minus to the 4th. You need that to the 4th because of that. Just make sure that you include your charges in there. If you look at silver, that silver ammonium here, and C. I put the whole complex ion in there and then put the brackets around it with the charge. So just make sure that you're complete about that. Please take note of all of the stoichiometry and make sure that you include that. It doesn't matter. This slide is just explaining that it doesn't matter where you start. Once you reach equilibrium, that's the equilibrium. So it will find it wherever you start your reaction. It doesn't matter if you start with reactants, if you start with products, they're all going to find their way to equilibrium. And that equilibrium is going to be the same. So what does K actually mean? If you have a K that's greater than 1, what that means is that my, remember, it's products over reactants, right? If you have a big number, that means that you have more of your numerator. I have more products. So that means if I have a K that's greater than 1, I can say my reaction favors the products. If I want more products, that would be a favorable K for me. If it goes the other way, there's a baby, where my K is less than 1, that means that my denominator is now dominant. So this number is bigger on the bottom, and I have a number that's less than 1, and my reactants are favored. I have many more reactants than I have products in that equilibrium reaction. Sometimes your K can equal 1, and what that means is that you have the same amount of reactants and products. It doesn't happen often, but it can happen. So if your K is 1, that means that your concentrations are equal. You can imagine that that's kind of a hard situation to find. The number is big. It's greater than 1. Your products are favored. If it's small, like anything times 10 to the negative 3 or whatever, if it's a small number, it favors the reactants. That's what K is actually telling us, which is why we care about K. Here in 4, you're given a K, and then in 5, you're given 2 different Ks at 2 different temperatures. So I want you to look at these problems and think about them, and then come back and we'll talk about the answer. Basically, we just have to figure out which is favored and how easy it is for a reaction to go in number 4. So if my K is 1 times 10 to the minus 30, that's super, super, super small. Very much below 1. If K is below 1, that means I favor the reactants, which means I have more of these guys, which means that N2 really doesn't want to be fixed. That's what it means when you take something that is atomic and you transform it into something that's more active. N2 is pretty inert. It really doesn't want to do anything. And the N2 bond is a triple bond. And it's a super strong bond. And so to break that takes a lot of energy. So nitrogen fixation is a really difficult process to do. So how feasible is it to fix nitrogen by forming NO at 25 degrees? Not very much. You really don't get any products at all. Okay, so for number 5, we have H2 plus I2 forming HI. At 298 K, I'm going to make a little temperature KP chart. At 298, my KP is 794. And at 700, my KP is 54. So what this little chart tells us is that at lower temperatures, my equilibrium value is higher, so I favor my products more at lower temperature than I do at higher temperature. Is the formation of HI favored more at higher or lower temperature? So HI is my product, so it's more favored here, which is the lower temperature. Right? KP goes down at the higher temperature, which means that my equilibrium is pushed in this direction as I raise the temperature. So the answer is lower because Kp is higher, which means I have more products than reactants. Okay, that's that. So solids and liquids are not put into a KEQ expression. They are non-compressible, so they do not really have any volume changes, and so they are constants. So they are not included in the equilibrium expression. So anytime you have a reaction that has a little S or a little L next to a reactant or a product, we keep them out of my KEQ expression. Their concentrations are not going to change, and so they don't matter. So KEQ expressions should only include no solids and no liquids. Don't forget. All right, so here we have some where now we have mixed reactions where we have solids, liquids, aqueous gases, the whole shebang. So I want you to write the equilibrium expressions. If you are omitting something, just leave it out. Sometimes you won't have a numerator, sometimes you won't have a denominator. You can put a 1 there if you want, if it makes you feel better. So try A, B, and C. This is not included because it's a solid. That is not included because it's a liquid. The gases are there. So just check your answers. This last one says that you can write a Kp expression. So if you did, it would look like this. That would be your Kp. Okay? Kp is based on pressures of gases instead of concentrations, and Kc is based on concentrations of gases or aqueous species. Kp can only be done if your whole reaction is gases. So we have a conversion equation that we can go from Kp to Kc. And we have to use the gas constant. This time we're using the gas constant in liters atmospheres per mole K. Your temperature has to be in Kelvin. Delta N is a change in moles of your gas. So I find how many moles of gas are in my products, and I subtract the number of moles in my reactants. You can get a negative number for delta N. You can have -2, you can have -1, you can have 1 or 2. You can have 0. If you have 0, then Kp is equal to Kc, because this whole thing would go to 1 if that was a 0. But anyways, okay. Let's do number 7. I have to find Kp given Kc. So my equation is Kp is equal to Kc RT delta N. I need to find what delta N is. I gotta figure out how many moles I have. My reactants have 3 moles, because I have 1 plus 2. My products have 2 moles. So if I'm going to do delta N, products minus reactants, 2 minus 3 equals -1. That's my delta N. I need Kp. Kp is equal to 5.4 times 10 to the 13 times 0.0821. I'm given my temperature is 298 Kelvin to the -1 power. So I take this thing in the parentheses to the -1, and then I multiply it by Kc. What I get for Kp is 2.2 times 10 to the 12. There are no units. I didn't even mention that yet. There are no units for K. Equilibrium constant has no units. So you can't forget them. Okay? No units. They all cancel out. I want you to try number 8. I'm going the other way. So in number 8, delta N is 0. So Kp is just equal to Kc, because your RT to the delta N term goes to 1, because delta N is 0. And so it's 6.2 times 10 to the 2. There's no difference. Okay, so now we are going to plug some numbers in once we get our equilibrium expression. Okay, so first I'm going to look at my equation. I'm going to notice that there is a liquid here, so I'm going to cross it out because I don't need that in my K expression. So I'm going to just write K is equal to, I need my products over reactants. I need to make sure I get that 2 up here. Perfect. Okay, so that's my equilibrium expression. It says calculate Kc if at equilibrium you have 1.2 molars of CO, 0.56 molars of HCO3 minus, and 0.56 moles of H plus. The important things are that we are at equilibrium. When you are at equilibrium, you can just plug those numbers right in. You have molarity, so we don't have to calculate molarity. We can just plug them right in. So I'm going to say K is equal to, so HCO3 is first, so 0.56. These are multiplied together, not added. I'm going to multiply that by 0.56, which is my moles, or my molarity of H plus, my concentration of H plus. And then I divide by my 1.2. Please don't forget to square that. We have to square it because of that square right there. And so the answer is 0.218. That's K. No units. That's it. That's your answer. Make sure that makes sense. All right, you guys. Try 10. You're calculating Kp first, and then you're going to convert to Kc. All right, and there's the answer to 10. Make sure those calculations make sense. And then you've got the same numbers. Okay, I'm going to introduce the rice table, which we are going to learn to love because we're going to have to use this for the rest of the semester. What it does is it organizes information so that we can figure out what happens over the course of an equilibrium reaction. You put in your initial information, you put in whatever you know about the equilibrium condition, and then we figure out what happens. Okay, so the R stands for reaction. So you will be given a reaction. Here it is. At a specific temperature, the reaction mixture initially contains 0.75 molar of CO, 0.125 molar of H2. It's important to understand that this is to just notice that this is the initial concentrations, and then we have an equilibrium concentration. And there it is. We need to find K. And then we need to determine, is K going to indicate that we favor reactants or we favor products? If we favor reactants, remember K is going to be greater than 1. If we favor products, K is less than 1. Okay, let's set it up. So I have my equation. Don't forget your stoichiometry. In my rice table, the reaction is the R. I'm going to put my little letters there. Okay, I think your book just does the ICE, but I like to put the reaction there too. I think it helps. So I is initial. That's any concentrations that we know initially. You always want molarity or moles, but I always use molarity in a rice table. All right, you don't use mass. It's always concentration, or like I said, you can use moles too, but I like to use concentration. So initially, the problem said that we had 0.75 molar CO, and we had 1.25 molar H2. The problem and most of the problems say nothing about how much of your products are there because you don't have any yet. We haven't made any because we haven't started the reaction yet. If you are given an initial concentration of products, then put that in. But if you're not, you assume 0 because the reaction has not started. The C is for change, so that's how we change over time. and E is my equilibrium, and that's what my concentrations will be at equilibrium. In this problem, we were given that the concentration of H2 at equilibrium was 0.53 molar. So I'm going to put that under my equilibrium column. Okay. The change rho is going to be minus or plus a value. And if you don't know it, it's X. So my reactants are going to decrease in concentration because there's only one direction that my reaction can go because I don't have any products. This is an equilibrium, so I need to write my equilibrium arrows in. Because this reaction only has one direction to go, my reactants are going to decrease. So that change is going to be minus some amount. We don't know what it is. So CO is going to decrease by some amount. And then this one is going to be minus, but it's 2x because for every time this reaction happens, 2 moles of H2 are being used. So I have to carry that down. And then this is going to be plus X because my products are growing in. What we are looking for is K. And remember, you can only calculate your equilibrium constant with the equilibrium rho. So I can only use this last one to calculate K. So if I write my K expression, it's going to look like this. Don't forget that little squared up there because of my stoic. What we need to do is we need to fill in my equilibrium rho. Luckily, I have this full row all filled in. So I can use that information and solve for X. So I'm going to say, okay, well, 1.25 minus 2x is equal to 0.53. So I need to solve for X. I'm going to subtract 1.25 from either side, and that gets me negative 0.72, and then I just divide by negative 2, and X is equal to 0.36. Okay, so I can fill in this by just putting X in. So my product, if X is 0.36, 0 plus 0.36 is 0.36. So that goes here. Okay. And then for my carbon monoxide, my CO, 0.75 minus X equals, remember, X is 0.36. And so you end up with 0.39. So I put that here. Now we have my equilibrium rho, the whole thing, so I can go ahead and plug that in and solve for K. All right, 0.36 divided by 0.39 times 0.53 squared. Don't forget to squared. And put this whole thing in the bottom in parentheses if you put it all into your calculator at once. K is 3.29, no units. The question, that's A. And then B asks, do we favor products or reactants? Since this is over 1, K favors my products. Don't forget to bring whatever stoichiometry you have down to your change row. So this was just 1, so that's 1. This is 1, so that's 1. And then also don't forget it to have it here. That's like the biggest mistakes I see people make. This is very patriotic. Okay, you guys do this one. Pause. Come back for the answer. Here it is. I made my rice table, plugged in my equilibrium row, made my K expression, plugged my equilibrium row into my K expression, and calculated K. It's below 1, so I know that it favors reactants. That is how you make a rice table. We're going to be doing this, like I said, for the rest of the semester, so get used to doing that. All right, that's it.